Welcome to another video about the basics of programming. This is Basti's Programming Corner, and today we are going to talk about reading and writing files. So files are a very fundamental concept when you work with computers and software. So you probably have several files on your personal machines, like music, text files, images, videos, and so on. And of course, there's a common requirement for you as a programmer to read and write files with your code. So that's why we're going to have a look at it today. What we're going to build is a very simple application that writes some item names to a file and reads from it, and we can add items, show them, and remove items. So as you can see here, I have a list of items which is actually written and read by my program. So I created a little program store, and by using the list action, store list, I can show the content. When I want to add some items, I just say store add, and maybe I add some juice to my list and lemon, because I want to make lemon juice later. Then I can show the new content by using the list action, and I can see it has been added to the end. I can also decide to remove some elements. Let's remove the banana, for example, because I don't need it anymore. And I can just type it, and list will show me my new list. And what is important about it, these items are actually stored in a file. So you can see it here. It is the items file, and when I look into it with some kind of editor, I can see the content. So we actually wrote it with our code. When I make changes in the file, it is reflected in the program too. And the nice thing about it is it doesn't matter that my program is not running all the time, and I can shut down my computer and restart it without losing my data. So that is the fundamental characteristic of files, right? That your data is stored permanently. We also call it persistently, and it's not just held in temporary main memory. Okay, so just to get you into the content, let's quickly talk about the content. I've shown you the example program as a demo, and we will look a bit at how to use command line arguments. These are the actions that you have already seen, like add, remove, and list. We'll also talk about constants. I will show you the switch case construct in Go. We will do some error handling and exiting the program in case of errors. You will, of course, learn about how to open files for reading, for example, but also for writing. And we will look at different ways about how you can read and write file content, because there are several options that you have here depending on your requirements and depending on the trade-offs that you are willing to accept in terms of advantages and disadvantages. So let's jump right into it. I just created a new directory in my Go path and called it item-store. There's only the README file in here, which is a scratchpad for the content of this tutorial. Now, if you haven't installed Go yet, feel free to look it up in the internet and then continue the tutorial. But since I'm assuming you already have Go installed, we can just create our file that we're going to fill with code. And this time I'm going to call it store.go instead of main, so it's a little bit more expressive, and we're actually going to compile and build the program later into an executable. Then we can just call it by using store instead of calling it main. Another thing that we're going to do is we're going to use the go module init command for creating the module file. I'm going to call my module item-store. So it instructs us to call go mod tidy. Now we got this go mod file here, which is it gets more important when you import external dependencies, write tests and so on, but just for completeness sake, I do it here. So let's start by defining our file in the main package, and we're going to import fmt as usual for basic output, and our main function is the entry point as always. We can print something like welcome to our item store. So save it, and you can run it as usual with go run and store.go, which prints our message. Nice, now we got our minimal project setup. Let's start with building the skeleton for the actions that you can trigger. So this is the command line tool that we're going to write. The usual procedure is that you enter some actions like we did here, and then the program does something, and when it's done, it just exits. So you find that commonly for system tools, depending on your system, be it Mac or Windows, Linux, whatever, you may know some system tools that work in a similar fashion. And this is very good for certain tasks, especially for more technical users and use cases where you don't need a user interface or something like that. Basically, the command line interface and the actions and parameters that we pass are the user interface in our case. Now, which actions do we have? We have add, list, and remove. So let's first define these. Of course, we need to detect which action the user triggered. And you can do that by using command line arguments. These are accessible via the OS package, which stands for operating system. And by accessing os.args, we get the arguments that the user is passing upon calling our program. So just to check them out, let's print them. And as you can see, there is one argument. It's actually a slice, os.args. And the first argument is basically the executable file that has been called. It looks a bit different here from store.go because under the hood, go run is compiling our program and then running it. It's doing this in a temp directory, which we do not really recognize because it's doing this under the hood for us for simplified usage. But that is a common thing when you work with command line arguments, also in other languages. The first argument at index 0 is usually the file that has been called on the command. So that is something to keep in mind. Now, when we actually pass some arguments like add banana, then we can see these are added at index 1 and 2 in the argument slice. And now we can make use of them. So at position 1, index 1, we expect our action. So we can declare and initialize a variable action, which is os.args at position 1. And let's see if this works. Yes, it does. It realizes our action is add. Okay. Now, of course, we need to make sure that we handle corner cases, like when the user does not pass any action. So let's say I don't yet know how to use it, or I just forgot it and call it like this. Then we're accessing an element in the slice that actually doesn't exist. So we get a runtime panic, which is Go's way of saying the program crashed for some unexpected reason that you did not handle in your code. And it shows us the location. So at line 11. And it says index out of range 1 with length 1. So as you probably know from one of my earlier tutorials, if the length is 1, there's only one element in the slice, and that is at index 0. So of course we can't access this non-existent position in the slice. So we actually need to make sure that the user filled that. So we can do that by checking the length of the argument slice. And we expect it to be at least 2, because the first is implicit, the program itself, as I said. The second is the action. So if the length is smaller than 2, then we want to inform the user. So we're going to say expected action argument. And what do we want to do if the user did not pass it? Well, we can't really do something useful if we're missing the action, so we probably want to terminate the program. And one common way to do that is to just exit it. You can do this with os.exit in Golang and pass an exit code. By convention, code 0 indicates success and non-zero an error. So we're going to exit with 1 because 0 would indicate success. That is the normal termination that happens anyway when you don't explicitly call it at the end. Now you could also write if-else cascades, but this gets quickly messy. When you have a larger program and more complicated logic, it grows quite quickly. And the more places you have in your code where you need to be careful and check for valid input arguments, the harder it gets to read. So it's usually a good idea to make these hard checks that are absolutely required at the beginning of functions where you can easily see them, and then do an early return, or in our case, an early exit. Since the program terminates here, we can save the else, save the nesting here, and this gets more readable and even structured when we extend it. So let's see if this actually works. So let's say I forget to add the action. Then I get my message expected action argument, and exit status 1 is automatically printed just as an information. In Linux, for example, I can also check the last exit code by using this command that says 1. For comparison, if we pass the action, like add. Then it does not exit, it prints our action, and the exit code is 0. Okay. And next, let's build the skeleton for the other actions. So what actions do we need? We need add, remove, and list. We can use usual if-else if constructs for that. But a common way when you have multiple actions, or let's say more than 2 or 3, and it's possibly extended in the future, is to use a switch case construct. Switch case is very similar to if-else. It's just more convenient for lots of options and certain checks. So you can write switch, then the variable that you want to compare, and then you can define several cases. And we can write case add, remove, and list. And you can imagine this is like an if-else. But you don't explicitly write the if condition. Then you would write if action equals add, else if action equals remove, else if action equals list. Instead, you write the variable or value that you want to compare and the different cases that are checked for equality. And once these get to a certain count, it's more clean to read and write this as a switch case. Here for 3 cases you could also argue that if else would be fine. One useful thing about switch case is you can define a default case that is executed when the other cases do not apply. So we can use that to inform our user about all valid actions. So valid actions are add, remove, list. Save and run. Let's say I write go run store maybe move, but there's no move command, and then it tells me okay, we know add, remove, and list. That is a useful feature of the default case. What else can we improve? It is usually a good idea to define constants for values, be it strings or integer values, that are repeatedly addressed in our code. So for example, you can see here we got them in the case distinction, and we also got them in this message for helping the user. So let's say sometimes down the road I decide to rename a command. Let's say we want to call remove, we want to rename it to delete. So I changed it here and I changed the implementation, but it's easy to forget that we refer to it in other places like other files and so on, or for example in this help text. And what happens then is that it gets a bit inconsistent. So the user of the new version wants to remove an item, And this is no longer a valid case since we renamed it to delete. So it runs into the default, but we didn't adapt the default. That is why it states valid actions are, and now the user is confused because remove is still in there. That is why it's a good idea to extract constants for these, let's say magic values that we refer to often, in order to have a single location where they are defined. This is pretty simple in Golang and most other languages. We can define them here at the top level. So these are somewhat global constants to this module. And I can call these, for example, action add. And the same for remove and list. So these are the constant names that we can refer to as a symbol and the value on the right hand side. And then we can just replace the literal values with the constants like we can also do for variables. And we can replace it here too. Let's do it like this. Let's see if this still works. Yes, it does. And now, when we got the same use case, let's say we switch from remove to delete. Strictly speaking, we only have to change this value here. And it immediately gets applied in all places where this constant is referred to, which can be in many places in your code, not just these two we got here in this example. But you can immediately see that I only have to adapt this place, and now when I say use the remove command, it is consistent immediately. It says valid actions are add, delete, list. So that is the value of using constants. As a rule of thumb, you should strongly consider using them when you refer to specially defined values like these actions in multiple places. If it's only one place, you could also just define them in line. Okay, now we got our action distinction. Let's start with reading a file. So we're going to implement the list action here. As you probably know, it's a good practice to extract functionality into separate functions for keeping your code nice and clean to read and maintain. So we're going to create a function that is called list and call it in the switch case. We don't really need any parameters since we know the action that shall be performed. And you can find basic file operations in the OS package too. So we are going to start with the open command. It accepts a file name and it returns a pointer to a file and potential error. So let's call our file for storing data items and assign a variable file and arrow as the usually defined variable for error checking. Now, one thing to keep in mind is that I/O work, like reading and writing files, can almost always return errors. There are several ways that this can go wrong. Let's say your hard drive is full, or maybe you don't have the access rights for the folder you want to write in, or something else. So that is why almost every operation associated with files needs some error handling. That is true for all programming languages. It's not just Golang. But in Golang, the standard way of doing that is the error return value, which you can then check. So what we want to do is, if error is not nil, which is the pointer that points to nothing, so nil would mean no error occurred, everything is fine. If it's not nil, we need to handle it. So let's print just the error for now. And for the start, let's ignore file by using the underscore character and see what happens. So it says open items, no such file or directory. That is a good example for a typical error. We try to open a file that doesn't exist yet. So what we need to do is either create a file or make sure it exists in any case in our program. And we could now create one for testing, but to make our program more robust, we could add a handling for that. So one easy way to do that is, instead of using the simple open, using open file. And this is a bit more complex, but also it has more options. Not only the file name, but also some flags which can specify more detailed behavior, and permissions for the file. So here it already says you can pass a flag oCreate, which will create the file if it doesn't exist yet. And that's what we want to do. You can also specify what you want to do with a file, like reading, writing, or both, which will then reflect in the operations that you can perform. So it's something that is communicated to your operating system when it gives you access to the file, what you want to do with it. So first let's give it the file name. Then we're going to specify the flag, and that is OS open create. And you can combine multiple flags by using the logical OR operation, which is just a single pipe. It basically combines bit flags into a combined bit pattern. If you don't know what it is yet, it's not that important. You can read it up if you're interested. Just remember that you can combine these by using the logical OR. So we want to read the file, so read only is probably a good idea here. There's also read write if you want to do both, or write only if you just want to write the file. So we communicate that you want to write and that the file shall be created if it doesn't exist yet. The last parameter is the file mode, and that specifies things like file permissions, and if this is a directory or a simple file or something like that. If you're using this on Windows, you're probably less familiar with it, but when you're using Linux, for example, there is a concept of file rights management where you can define which user and user groups have read and write access to which files. So I don't want to go into the details too much, but you can read it up if you want to. I'm just using flags 0664. In my case, it basically specifies that the user and the group of the user can read and write this file. Other users which are not in my group on my operating system they can read it but not write it. So let's see if the error still happens. We don't have an items file here. And it works. As you can see, we just created an items file that is probably empty because we didn't write anything. But it's a good practice to make it this careful, because now we expect the potential case that the file that we want to read doesn't exist yet and we are creating it. So it's a good idea to make it this robust. Now in the error case, we probably also want to exit because we can't do anything in this case. So exit with an error code 1 is probably a good idea. We don't want to continue the program when we couldn't read here. Actually, let's make a function out of it to keep repetition low. And we're going to call it exit pass. Are we passing a message or an error? Let's pass an error. We're going to print this error so the user can actually see that something went wrong. And then we're going to exit the program. Now I can use this little function called everywhere where I want to check error. And of course, we also need to make sure we're just using it if error is not nil, because otherwise the operation went fine. And now I can use, let's call it check instead of exit. I can call check error after every IO call where I have some error handling to do and simplify my code. Okay, now we got an actual file descriptor. And we can use that to do some things. First, let's do a low-level read. So we're actually going to read bytes from the file into our memory. Then afterwards, we will replace it with some simpler approaches and more high-level approaches. So as you probably know, files consist of bytes. And you probably have an idea about how much space files need on your hard drive, for example. Like text files need very few space, usually when they're not too large, like only in the kilobyte range. And when you have music or videos, they can have megabytes or even gigabytes. So the usually smallest amount of storage is a byte, which consists of 8 bits, and a bit is just a true or false, 0 or 1. So everything that can be written and read to files, network, and other I/O resources is basically broken down into bytes. That is why all these operations usually operate on byte streams or byte slices, for example, in the case of Go. And you can see there are several operations, methods, so to speak, on file. There is this read method. It takes a byte slice. This is where the bytes get read into. And it returns the number of bytes read and an error. So we can use that in order to read bytes. We will create a content byte slice by using the make built-in function. And now the interesting question is, how many bytes do we want to read? That depends on the file and how we want to process it. If it is a large file, it could make sense to read only a few bytes per read. But if we want to keep it simple and if we have small size, we want to read the whole file into our RAM, into our main memory. But how many bytes are in there? I mean, we can just use a byte array which is probably large enough. So let's try this, passing content. And we assign count and arrow. Then we're going to print how many bytes have been written, read. Printf. Going to check for error, of course. Print the count and then the actual content. And how can we print the content? Let's just try it out. And for us to actually see something, we should add some items here. Let's say banana, book, and coffee, and save it. Go, of course. Go run. So we chose action list. We read 18 bytes, that is the size of the file content. And here you can see the bytes. So this is actually a slice of bytes. You can see the end, there are zeros, a lot of zeros. That is because our byte slice that we created an allocated space for, it is actually larger than we need, as we guessed. So that is the reason for the zeros. And these bytes here, these are Unicode characters. So Unicode is an encoding for characters for text. And this is stored as bytes. Now instead of printing bytes, we want to actually see our strings. So it's pretty straightforward to interpret these bytes as UTF-8 encoded strings. We can just go to the content variable and do an explicit type change to string. And let's see what happens. Now we actually see the content. So here's a new line missing because we didn't include it. But now we see the actual content. So you can see the byte slice is interpreted as UTF-8 encoded strings. And we actually see the content of our file. Now this was fairly low level reading. There is still the issue of how much byte space we need for reading. So the list grows and I don't really know how much space I need. Let's say we underestimated the size. Here it says read 18 bytes. Let's say we just got 10. What happens is that we actually read less than is in our file. So we can see here that book is cut off because we only read as many bytes as we provided. We provided a byte slice of size 10 for reading, and file.read will read up to len bytes. So one thing to solve that is we can determine how many bytes are stored in the file and then make the size of our byte slice accordingly. You can do that by using file.stat. It returns file statistics, file info object, of course an error, potential error that we need to check. And it has some pretty useful fields like the size, which returns the byte count of the content. You can also check other attributes like is this a directory or what is the actual name and so on, modification times, but we're interested in the size. So we can say file size in bytes is info.size, and then we can make sure our byte slice is big enough to hold all the content, but not larger than needed so we don't waste any memory space. And let's see if it works. Okay, file size is 18. We read 18 bytes and it matches our content. So let's say our list grows over time and now I got another item like lemon. Our program behaves as we expected. We don't have to adapt the size. It automatically detects, okay, size is 24 bytes. I'm going to create a 24 elements byte slice and it perfectly reads it in. So this was an introduction to reading on a lower level and talking about byte slices and file sizes. There are convenient functionalities for making this simpler that I wanted to make you aware of. But of course it's useful to understand the basic idea of byte slices and how you can read files. Because we can simplify that when we don't have to write so much code about reading the size and so on, because this is a really common task. There are several different ways to solve that. So one way to do that is to just use os.readFile. ReadFile expects a name, and as the documentation says, it reads the name file and returns the complete content. So it takes care of creating a byte slice that is large enough for the content. So we can just replace our old solution with that call. Then we also don't have to worry about the additional parameters for open file. And then we don't get a file descriptor. Instead, we get the content of the file. And this already gives us the byte slice. We can print it after string interpretation, and let's see if this actually works. Yes, it does. And as you can see, it's much simpler. 3 lines of code only, because this is a common task. And it is well suited when you have rather small files where you can read them completely into memory. If you have huge files, you should probably choose another approach and only read chunk-wise, because you don't want to hold gigabyte-wise memory in your main memory. Okay. One thing that I wanted to mention too, let's quickly go back to our old solution, is that whenever we work with files, we need to think about resource cleanup. So since this is a resource that is given to you by the operating system, whatever operating system you're using, we have to tell it when we are done using it, and it can be cleaned up. So while you are working with this file, while you call it open, the operating system is granting some resources to you for working with this file. Now there are some limitations. You can't open an unlimited amount of files on a system because of resource usage, for example, or other restrictions. So it's important to actually tell the operating system when we are done and we no longer need it. This is done by calling close on file. So as you can see, it closes the file, rendering it unusable for I/O. And even that can return an error if it has already been called, but I think we don't need to check it here. So this is something to keep in mind, especially for long-running programs or programs that do a lot of file I/O. If you forget to do that, you might get system errors or bugs at some point, so that is something to watch out for. And there's another catch here. It might happen that you don't reach this spot here at the end because you go into another function inside, or you have an early return, or let's say you do some other logic. That is where the defer statement comes in. Defer is very handy for scheduling an operation that happens when the function is exited. So you can say defer file.close right up here, right after opening and checking for an error. And it will make sure that your close call is run when the function exits, so at the end. But we can specify it right here so it's not forgotten and it happens no matter what. So schedule cleanup when the function is exited. Or let's say function is done. So even if I do a return in the middle of here, let's say if, I don't know, maybe let's say I say something like is dir, then I want to exit here, then my close call here at the bottom would not be executed, and that can leak resource usage and make problems over time. But by using defer here, I make sure it is definitely run. So it doesn't matter if the function is exited because it's has come to the end, or because of an early return or whatever. The language makes sure that close is called when the function is exited. So let's actually verify that, and we can do that by extending this a little. I'm going to pass a function instead. That is printing for us to see what happens. And as you can see, it's printing all the usual stuff here. And at the end, it says closing file. So this is actually executed here, and it makes sure that the file is closed. To illustrate that this also happens when I exit the function at another point, let's say I do a return if info dot this dir is false because we don't have a dir here, then we just return. And as you can see, we are skipping the printing because of an early return, but the file is closed anyway. So that is a good practice in Golang and programming in general, to always make sure file system resources need to be released no matter what happens, to prevent system errors later when your system is out of resources, for example. Okay, now one benefit of using this more higher level approach of using read file is that it actually handles the file opening and closing for us. So we just get the content. We don't even have to worry about file closing. Very comfortable. That is how you can read simple files. Now let's say we have a larger file and we are not willing to load the whole memory into content. What you can do instead is you can use a buffered approach where you read the file in chunks. So maybe you read it line by line or multiple lines at once. And by using it that way, you make sure that you're only holding a small portion of the data in your computer's main memory, which is a good idea for larger files. Now, just to illustrate how this can be achieved, we will do it here, although our list is not that big. So the alternative is to use the buff.io package. Buff.io has types like buffered readers and writers. And one thing you can use is the scanner. Scanner is a type for, basically buffered reading. We need to pass a reader. This is an interface. I referred to my tutorial about interfaces to learn more about what interfaces are. And it's returning a pointer to a scanner. So what is a reader? Well, files, for example, are readers. So we can just pass a file here. We have to make sure that we actually open it. So again, we are going to do os.open file. And I'm using the more robust approach for creating the file if it doesn't exist yet. We just want to read it. Read only. Now, in the previous tutorial, I believe it was about basic data structures and reading text, we briefly touched on the scanner type. So how can you use a scanner? Well, let's first assign it to a variable. You can call scanner.scan that returns a Boolean flag. It returns true when the next part has been scanned, and false if it didn't because of an error or because we reached the end of the file. So we can easily use that in a loop and repeat that. And while scan is successful, we read the text as a text method for getting a string. And we just want to print that. So now we only have to tell the scanner which portions it shall scan. So maybe you want to scan word-wise, or in our case, we want to scan line-wise. You can do that by using scanner.split, and it accepts a split function. So you can define your own split function if it's something more exotic. or you just use the predefined. So there is a scan bytes, scan lines, for example, and we actually want to scan lines. So it tells you it is a split function for a scanner that returns each line of text, and it strips the trailing end of line marker like a new line. Let's try that out. And that didn't work yet. Just tells us the list, but not the items. And that is because it recreated the file. Okay, I passed the wrong file name. It is items, not item. So again, this is a good point where you should extract a constant, so you don't make these typo mistakes like I did. And you can see it worked. So we just created the scanner, told it to split line-wise, and then we can scan until the end has been reached or an error occurred and print it line by line. And by using that, you only hold one line in memory in each iteration, which is good for, let's say, larger files. For completeness sake, you should also check if scanner had an error. So when scan returns false, it might be due to an error, and that is why we should check this afterwards. Yeah, so that is a simple way of buffered reading by using a scanner. Now let's do what I already touched upon and create a constant for this file name, because we're going to refer to it in many places. So just const, we'll name it data file, that is items. And now we can replace it here and here, so I don't make any typos anymore. If you have quite a lot of constants, you can simplify the definition a bit by using this notation. So I can remove the const keyword from every definition and just enclose it with parentheses and constant. It's similar like the import, where you can say import buffer.io, import fmt, import os, and so on. And you can just bundle that and avoid some repetition here. Yeah. So that's about our list implementation. I think for our small list, it's okay to just use the first approach. First approach reads all file content into memory, which is fine for smaller files. Second approach reads file line by line, which is better for larger files. So I'm going to put the scanner option in comments so we can check it again later, but I will keep the very simple three-line solution here. Next, let us write some content to a file. So we're going to implement an add function here. Well, what do we need to actually make this work? we need the item names that the user wants to add. So after the argument at index 1, there can be one or more item names that shall be added to the file. And we can access them by using the slice operations. So we can use the notation where we specify a subslice. So by slicing the slice, we get a sub list of this slice. We want to start at index 2 inclusive until the end in case there are multiple. So by using a colon and omitting the second index, we tell the language to slice from index 2 until the end. And then let's print it just to check if it works. I'm going to add lemon and grapefruit. And you can see we got a new slice which is a subslice of the original argument slice. And it has the elements that we passed. So even if I add another one like ketchup, I get the third one too. And as before, we need to make sure to catch any errors. So if I forget to add an item, I actually get an empty slice. So we should probably check for that and inform the user that at least one item needs to be specified. We can do that with a length check as usual. And if that is, if it's 0, then we actually want to inform and exit. So expected at least one item name. Since we've written this print and exit multiple times now, it's probably a good idea to create a function for that. And we can call it exit. We pass a message, which is a string, and we print the message. And exit with an error code, which is 1 for us. So then we can do it like this. And again, since we are terminating the program here, we don't have to do so much nesting by using if-else constructs. We can just continue our code here. Let's use exit at the other place too to avoid some redundancy. And we can also use it in our check function by just calling exit and passing the error as a string. There's this error method that returns a string. So let's move these little helpers to the bottom for readability and keep the actual logic up here. And now it says, okay, expected at least one item name. And once we provide that, it's all good. So then we can pass our item slice to the add function, and that is all we need. So we create the function with an items slice of type string. And now we actually want to write a file. So we already got this test file here that we created manually. Let's remove it because our program has to be good enough to actually create it itself. So again, we use the OS package, and there are several options here. We could use new file, or just create file. So we can create a file by using create, passing the name, again using our constant data file. So we get the file descriptor and the potential error that we need to handle. Now we created a file. As we already learned, we should make sure to schedule the closing at the end of the function to release the operating system's resource that we acquired for that. And now we created a file, so we can actually write into it. And one simple way to do this is to just use the write methods on the file type. So here you can write a slice of bytes, or you can also write a string that will handle the byte conversion for you. So let's call write string for every item that we got. So we are using a for range loop. Ignore the index, we're just interested in the element. Pass the item. And we want to add a new line so that each item is actually placed in an own line in the file. So we do the string concatenation by using plus and \n for our new line separator. Our write string returns the number of bytes written, which is not that interesting for us, but we should definitely check the error in case something went wrong. Oh, I forgot the range here. Range. Okay, so we created the file, we checked for errors, we made sure that it's closed at the end, and for every item that the user passed, we write a string terminated by a line change to the file. So let's see what happens. Right now we don't even have an items file. And now when I create one using some item names, let's see if the file has been created. And yes, it has. The items are in there, separated by a new line. And you can see there's an empty line at the end because of the new line after the last element too, of course. So we can also check it with our list action. So when I specify list, yes, I get every line in there. Of course, I also get the last empty line, which is a bit unfortunate for our output. It doesn't really bother us in the file because we terminate each line. But for printing, I guess we should filter that. And here we're just using the whole content for printing. Now we could split the string by a new line, or we could remove the end. So Let's see what we think is simpler. There is a strings package that has some helpful functionalities. Let's see, there are probably some trim space. All leading and trailing white space is removed. So I'm not sure if that removes a new line. We can check that out. Yes, it does. Okay, so that's pretty simple, right? We don't even have to do much splitting, we just trim the spaces to clean the output. Now back to our writing. As you can see, it works. But what happens when we already have a list and we want to add more items? So I'm going to add some coffee here. Okay, that seems to have worked. What does list say? And as you can see, it recreated the file. So it just overwrote our old file and wrote something new in it. But we don't really want that, right? We just want to append and not create completely new files. So this can be achieved in different ways. First, let's do it by navigating in the file. So instead of creating a new file, let's use open. And again, I'm using open file to create it if it doesn't exist yet. So I can copy that from here. We're going to create it if it doesn't exist yet, but read only is the wrong flag. So let's actually see if that fails if we run it. Yes, it does. Bad file descriptor. Why is that? Well, we told the operating system that we want to read the file only, so we get a file descriptor that allows reading but not writing. So instead we want to write here. And now it works again. So that was a good test for us. Next, we need to make sure that we're actually writing at the end of the file, and that can be achieved in different ways. I will show you one way first, and that is using file.seek. You have to imagine that there is a position in the file where you're currently at for reading and for writing. So when we open the file, we are automatically at offset 0, so we start right at the beginning of the file. And each time we write, we move this position forward in the file, so byte by byte, and in the end line by line for our case. By using seek, you can modify the position where you're at. The documentation is quite clear about that. You pass it the byte offset for the next read or write operation. And there's a second parameter whence, which specifies the interpretation. So you can say I want to interpret this offset from the beginning of the file, the origin, relative to the current, or even to the end. So what we can do here is to specify 2 to say we want to seek to the end. So offset is 0 but it's interpreted from the end of the file. And it's actually returning the new position and an error. So let's assign that. Check for error, as always, and print the position. Now we're going to add some eggs. Let's see if it worked. Yes, it does. We still have the coffee entry from earlier, and we added eggs at the end. And the position of the seek is 7, so after 7 bytes, we were at the end and could add more items. So let's try again, add some banana and lemon. So after X we had position 12 at the end of the file. And we just added the other elements. So seek can be used to navigate inside the file for placing yourself at a certain position for reading or writing. So that is one way to do the appending. Another way that is a bit more simple is to specify for the operating system that you want to append to this file. You can do that by specifying the flag append, and that will immediately give you a file descriptor that is suitable for writing at the end, so you can't even modify the earlier content. And that allows us to omit the seek code, and we don't need that anymore. And we can immediately start writing at the end. Let's see if it works. We're going to add a bagel and some cheese. And it worked perfectly fine. So there's no need in this case to do the low-level seeking in the file. Okay. One more thing I wanted to show you is how you can use buffered types too for writing. So this is very plain and simple when you want to write data. And every write call that we do here will actually do the hard drive access and write data to your file. Now, if you're writing a lot of data, if it has large memory consumption, or if you do very many high-frequent small writes, it's more efficient to actually use buffering again. So the concept is similar to what we did here when we used the scanner. Instead of writing every little piece of bytes, we write in chunks. So every time you have a certain chunk ready, you flush that to the file on your disk, and that can be more efficient for large files and for files where a lot of small writes would happen otherwise. And again, buff.io is our friend in this case. So buff.io has a writer type. You can create one with new writer, and you pass it another writer. So a simple writer is a file. And this new writer will internally handle the buffering for us. So we actually have a buffered writer. And we can use it very similarly to the direct file access. So you can also say write string. So it looks very similar. But the difference is it is only going to trigger your hard drive on your system once the buffer has reached a certain amount of being filled. And that is why we need to make sure that we actually tell it to flush at the end. So it will flush to memory, to persistent storage when the buffer is full, or when we explicitly say flush it. And you have to remember to do that, because at least the last write attempt will probably not fill the buffer. And you want that even the last few bytes that you wrote here are actually persisted and taken from your main memory to the actual file on your hard drive. So that is why with buffered writing we need to remember calling flush for takeover of in-memory data to hard drive file. That is what flush does. Of course, we also could get an error here when, let's say, your hard drive is full or whatever, so we should better check it. And we won't notice a big difference here. It's just basically doing the same from a user perspective. When I add some donuts, for example, and orange. It will just write it out. So there are more options to configure this. You can, for example, specify how large the buffer is and some other things. But for simple use cases, the default settings are usually fine. Okay, now we learned how to write files in a very simple way. Let's complete our program by adding a remove function, and this is where we need to combine what we learned about reading and writing to actually remove certain parts of the file. So let's implement the last operation that we need to complete our little program. So for removing, it basically is the same when validating the input. We expect at least one additional argument, so we use a subslice from index to on. And if that is not given, we inform the user and exit the program. So expected at least one item name to remove. And here, let's say expect at least one item name to add. And then we can just call our function. Pass the items slice. So what do we need to do in order to remove items that are in our list? We basically have to read the complete file. We need to run over every item, so over every line. And we just want to keep the ones that are not specified by the user and rewrite the file. So we probably have to rewrite the whole file. So first let's read the whole content. We already learned about the function read file, which pretty much does what we want. without too much to do from our side. So it returns the content on the potential error. The content is a slice of bytes, and we can interpret that as a string and separate it into lines. Another way to do that is, well, we could use a scanner like we did before. This is a very comfortable way. We can also use string functions. So I'll show you the strings version here. So let's say we start with strings. We want to split content, which is shall be interpreted as a string, and we want to split line-wise. So \n is our line separator here. Then we got the lines. And since there's always this last line, which is empty, we also get this as an element. But of course, we don't really want to handle that, and we can easily do that by trimming. So we can say strings.trim. That removes leading and trailing spaces like new line. Let's see, something is not right here, not enough arguments. Okay, so it's actually a trim. You can specify different things to trim, and we want to trim space. So yeah, trim for removing empty line at the end, split for converting lines into slice elements. So then we got our lines. And just to make sure this works as expected, let's print it and try it out. So at first, I'm not passing an item to remove, and of course I get an error as we implemented it. Now I am passing bagel, and it states our lines that we read into a slice that we can then use to process it. And you can see there are all elements in here without the empty line. So next we need to differentiate if an item shall be kept or not. And what I am first going to do is to put the items that the user specified into a map. This is because otherwise we have to do quite a lot of nested looping. So imagine we iterate over the elements here, so the actual lines, and using a simple for loop. Now we want to do the following. If line matches specified item, it shall not be kept in the file. And how do we check that? We would have to search the items slice, which means another loop. And as you may know from one of my earlier tutorials about basic data structures, nested loops can become a performance bottleneck when there are thousands or millions of elements. It multiplies in an exponential way. That means if our list is very long and we have a few items, that the number of steps that the program has to run is quite large. So let's say we have 100 items in there, and when we specify only one item to remove, it's pretty simple. It's only 1 times 100, so 100 steps. But if we specify 10 out of 100 items, we already got 10 times 100, so 1,000 steps to find the elements, to just find them. And of course, the bigger it gets, the more inefficient it is. A simple way to solve that is to just convert our input to a map. So we are going to create a map that is called remove. This is a map from type string to bool. So initial size is going to be 0 fars. So the key is the name that we look up, and bool just says, yeah, if it shall be removed or kept. So now for every item in the range of items, we put the item in there and assign true. So in essence, it is a set. We just want to have a set of items that need to be removed. There is no primitive set and go as far as I know, no built-in set type, but you can easily use a map for that, so it's not a problem for us. Now we have a map where every contained element is actually to be removed. And we can easily check for every element in our lines slice if it is in this map. So if remove, look up the key by the current line. So lines from index or at position index. And if that is true, we shall keep it out of the newly written file. So instead we invert this, and if it's not in there, we keep it. So if line item is not contained in map created from user specified items, it shall be kept, otherwise removed. And now we just have to rewrite the file. So we already read the complete content. What we can do now is to open the file and basically empty it. So let's do this. We're going to use os open file. We have to specify some flags because we want to do reading. We'll just copy it from here. At this point, we just want to write, so write only is okay. We don't need the read. Create is a good idea because it might not exist. We should also check this up here. But we don't even want append. We want to start right at the beginning of the offset, byte offset. So check the arrow. Make sure that we schedule the close of the file. And then we can write line by line, but first we have to make sure that the file has been emptied. And you can do that by calling file.truncate. And truncate says it truncates the file to the given size. It does not change the offset, so where you were at in the file when you did some seek or read-write operations, but it changes the file. So when we pass 0, basically empties the file. We didn't really move yet inside the file, so we don't really need to seek. Otherwise, you could just say file.seek to go to the beginning. I guess we can omit that here since it's not really needed. We are at the beginning. And now we can actually write the files, the item lines that we want to keep. So we can just say file.write string and then the line. So I'm going to extract that here. So this is the item that we want to keep. If it's not in the remove map, or let's say if it returns false because it's not in the remove map, then we write it and we need to add the line separator again. Let's see if that works. So our current list looks like this. Now when you remove eggs and cheese, let's see what we got. Got coffee, okay, eggs is no longer in there, and cheese has also been removed. So it works. Wonderful. So what we actually did was we read the complete content. We split the content into separate lines. And then we opened the file for writing. And we wrote each line into the file that shall be kept and not removed. So in a way, we are emptying the file and rewriting it. And of course, we have to do that because, we're not just appending bytes at the end of the file, but we need to rewrite it completely to account for all potential removals. Now, there are more ways to solve that issue. And what we could also do, instead of emptying and truncating, we could say just create a file. So we could say os create and that is an alternative. So it could be a bit simpler. Then we don't have to truncate here, because we just overwrite the file. We created a new file and we can we can write to it without having to worry about truncating. Let's see if that works. We got this inside and I'm going to remove orange and banana. And yes, it worked. So that's another option and probably a bit more simple. Now what we can also do is, instead of reading a string here and splitting it, we could use a scanner. So let me show you how that would work. Again, we use our buff.io package and create a new scanner. The scanner expects a reader. What is a reader for files? Well, it is basically a file that we need to open. So let's say we open it for reading. And then there is a file here. We make sure that it's actually closed. We pass it to the scanner. So we can put this in comments. Now that we have the scanner, we can say split by line, scan lines, and it's basically similar to what we did in the list implementation. So scanner dot scan returns a boolean, and while it returns true, we can just fetch the text. And then we could read it line-wise, and for every line we could check if we shall keep it in the file or not. Now, one important thing in this solution is we can't read and write at the same time. So while you can open a file for reading and writing, it would not work to read a line and then write a line and then read a line and write a line, because we are modifying the file by writing, and then our read would be problematic. So you have to separate it. We would read into a slice first and then operate on that slice and write afterwards. So that would be the approach here, just to give you an idea about it. But I think our string version is good enough here. So I will return that to the old implementation, which is a bit more simple. Yeah, that's about it. We implemented our functionality. At the end, let's just check that everything works as expected. You can add items like some T. We can list them and we can remove them, also from the beginning and the end, which could be a corner case. But it works as expected. And at the end, let's try to completely clear it. So I'm going to remove donuts, lemon, and bagel. And as you can see, it works. Now the list is empty and I can start adding things again. So one more thing I wanted to show you very quickly is that you can also build your Go files into a self-contained executable. This is especially useful for these command line tools, or when you got a product that you actually want to ship. Because Go Run is a tool basically for development, right? You got your Go files, you can pass it, and it's going to compile it under the hood and run the program. There's nothing wrong with it, but when we really want to use it and we need to type some things, it's helpful if we can simplify that and don't have to type Go Run. So you just say Go Build, then your file, and it very quickly compiles it and creates an executable. As you can see here, it's called store. There's the asterisk, which says it's executable. It has a few megabytes because it contains the whole runtime environment, like the Go runtime environment, garbage collection, and so on, and standard library functions. But now you can use that everywhere as long as it's the same system. Like I compiled for Linux, so I can use it on Linux machines without any external dependencies. I can call it like this and then pass the arguments. So it says expected action argument. And now it's a bit shorter to call, and I can basically do the same things like before. As you can see. Okay, this is it. We implemented all three functions. And to shortly summarize, you learned quite a lot in this video. I hope you can make use of it and program along with it, or tinker with the program, grab the source code, build it yourself, or think of a little program that you can practice on yourself. As always, I highly encourage you to try it out, because you don't learn programming from just reading or watching. You need to apply this knowledge yourself and experiment with it, tinker with it, try things out, and then it becomes part of your skill set. So you learned what constants are. We talked about command line arguments, how you can access them. We introduced the switch case construct, which is an extended if-else form if you want. And there are early exits in your program because we need to consider error handling as always. Every good program needs to consider error handling. We learned how to read and write the content of files in several ways. We learned that you can open files for reading, for writing, for appending, for different things. You need to release system resources when you're done with them by using close. Defer is a very handy tool for that in Golang. And apart from plain writing and reading, there's also a buffered version for almost everything in the Go standard library. So you can actually do this more comfortably and also for larger files in chunks. When you use readers or writers, you actually use the standard interfaces in Golang, which are defined as readers and writers. I encourage you to check them out because you will find them very often in Go and similar constructs in other languages. When you know how these interfaces work, what a writer is and what a reader, you also can use many more functions, not only for writing files. You can also write to network connections. You can, for example, create web servers, and they also expect readers and writers and other things. So everything that is I/O related, you often encounter these reader and writer interfaces. So that is it. We covered quite a lot. I would really like to hear from you how you liked this tutorial, what you found good about it, and what you would like to have changed next time. Feel free to leave a comment for me in the comments or subscribe, like, if you found this helpful. Thanks. See you next time.